continuing with this quotient construction, you need to prove this lemma. You take two cosets C and D in the abelian group R mod I. Let C prime be two elements of capital C and D prime be two elements of capital D. Then I want to show that the coset of CD is the same as the coset of C prime D prime. And the proof of this is exactly where the property that I is an ideal comes into play. We had a similar lemma in group theory, and that's exactly where you needed the fact that the thing that you're quotienting out by is a normal subgroup. Okay, since C and C prime are in the same coset, what does that mean? That means the difference is an element of I, meaning C prime is C plus some element of I for some A in I. And since D and D prime are in D, D prime is D plus some element of I, calling it B. Yeah. So now if you multiply C prime and D prime, you get C plus A times D plus B, which is a sum of four things. If you multiply out, CD plus CB plus AD plus AB. And now you just notice that these three terms are all in the ideal, because this is in the ideal because B is in the ideal. In I, since B is in I, and since I is a two-sided ideal, so in particular it's a left ideal. So you take a thing in I and multiply by some ring element on the left, it's still going to be in I. This is in I since A is in I, and since I is a right ideal. And same for this one. You can say either for this one. So in any case, the second, third, and the fourth term are all in I, and so their sum is in I. Since I is a subring in particular, so it's a subgroup in particular. So C prime D prime here is CD plus some stuff that is in I. This thing here is in I. Which means C prime D prime minus CD, which is the sum of those three terms, is in I. So C prime D prime and CD are in the same coset. And that's the lemma. Okay. And now once you have this, you're good. So definition, we are ready to define the multiplication given C, I'm calling them capital C and capital D. Capital C and capital D, two cosets. Choose a representative from capital C and a representative from capital D, and define the product of these two cosets to be the coset of these two representatives. The lemma above shows that this is well defined, that this thing is a well-defined binary operation from R mod I cross R mod I to R mod I is a well-defined binary operation, and verify that R mod I becomes a ring with these operations and pi, our pi up here, R to R mod I is a surjective ring homomorphism. This pi. Definition is back here. And its kernel is I, of course. And so what that means is that i.e. a plus I times b plus I is indeed ab plus I for all a, b in R. And finally, if R is unital, so if it has a unit 1, if R has a unit, oh, we don't call it unit, identity. Identity 1, then R mod I has an identity and its identity is going to be what else? The coset of the identity. If R is commutative, then R mod I is commutative. Etc. So next we have to give some examples, do the first isomorphism theorem.